Let's take a look at this new equation. It's fairly complicated. Make sure you understand the steps that I took to get here. It was combining the compatibility equation with the equilibrium equation, putting them in the identical format. So we have stresses on the left-hand side, and we have body forces and a material property on the right-hand side. To tighten up the notation, we introduced this Laplacian operator. It's called a del, so it's an upside-down delta. And a del squared means that you take something and you differentiate it twice with respect to x and twice with respect to y. That's what del raised to the power 2 means. It's an operation. It's a sophisticated derivative. It's a multi-step process. So del squared of this parenthetical term is equal to the right-hand side. And then we get another simplification. If the right-hand side is 0, and there are really two scenarios where the right-hand side is 0, I'll ask you to think about that shortly. Then we have a very, very nice, tidy equation in here. And this almost is t-shirt worthy. We're going to take it one step further, and then it becomes a t-shirt. So this is our governing equation right now. So let's take this next leap here, and suppose there was some kind of magical function phi. Phi being a function of x and y. But this is so magical that if you differentiate it twice with respect to y, out comes sigma x at any x and y. And to further make your heads explode, this magical phi, if you differentiate it twice with respect to x, you get sigma y at any x and y. And for no extra charge, one day only, we're going to provide a special. If you order phi right now and differentiate it once with respect to x and once with respect to y, you get the negative of the shear stress. Now this is a pretty sophisticated function that it can do all of that. So let's see what's going to happen. If we say partial squared partial x squared of sigma x, we're going to sub in this new function in here and say sigma x is partial phi partial y squared. We're going to say sigma y is partial phi partial x squared. All of that is once operated on the x, and the same thing happens on the y, and we're going to make this simplification where the right-hand side is 0. So we have this equation down here. Then, just cleaning that up, instead of saying partial squared, we have partial to the fourth of phi with x squared and a y squared downstairs. We have a partial fourth with respect to x 4 times. We have a partial fourth with respect to y 4 times. And then we have another one with x squared and y squared. And of course the bottoms doesn't matter here. The derivatives, the order of the derivatives does not matter. And we have this cleaned up expression, and this is truly t-shirt worthy. This is known as the biharmonic equation. So this is it in compact form. There's a cross product in here, which doesn't show up in the where it was raised to the second. So be careful. So you could use this bubbled form of the biharmonic, or if you could keep it all in your head straight, use this form of the biharmonic. And then, what is this magic function that does all of these incredible things? A function phi that satisfies this biharmonic, it's called the Airy stress function, and it was named after Professor Airy in the mid-19th century. So, the equation of compatibility and the equation of equilibrium here for plane stress and a specific set of boundary conditions allow us to get a complete full field expression. Remember, we're talking about a complete field for x and y. So we know the stress at any point. And then I want your heads to explode a little bit more. Remember when I brought this back and I said there were 2 reasons why this might be 0. Can you hit the pause button and answer why there might be 2 reasons? So the first reason, of course, is that if the body forces themselves are 0, then they drop out. But the second one is if the rate of change of the body forces are 0 with respect to x and respect to y. So if the rate of change of body forces are 0, then we have the simplification on the right-hand side. So that's really, really nice. The other amazing thing is that we have a stress situation that is independent of the material properties. So with the presence of body forces, the material properties must be here. Without body forces, the material properties are gone. This relationship is independent of the material, and that's a big, big deal.